So yesterday we started with our discussion on spanning tree protocol. So before we jumped into the spanning tree protocols discussion, we understood or we discussed what is a loop. Okay. So we considered three switches which do not have any MAC addresses in their MAC address table, and we saw how a loop may form when a particular device or a PC sends sends some information, right? And if loop is present in the network, meaning that all the switches are connected to each other, and there is no loop-free environment, no loop-free environment, right? We may see a loop in the network. So when a loop happens, we know that multiple copies of the data is circulated in the network, and the same copies do not reach the destination, and because they do not reach the destination, the MAC address table is unstable for all the switches. And because the MAC address table keeps updating, as well as all the copies that a switch reads has to process it, so the CPU utilization of the switch also increases. This is what we saw. This is what we saw. And collectively, these phenomena are called as broadcast storm, right? And in order to avoid this broadcast storm, we can create a loop-free environment by removing one of the links. Okay. And if there are many switches in the network, right? Like a data center or an enterprise network where there are many switches, and if we have to manually disconnect the links between different switches in order to create a loop-free environment, it's basically taking a risk of losing a network, of losing some users, or creating different kind of loops, right? So there are different reasons why we don't take that risk of manually disconnecting the link. So for that purpose, we created a protocol called as spanning tree protocol, right? And as the name suggests, it's basically a tree, right? It's kind of a tree, virtual tree structure. And in a tree, we know that the root is a very important part, right? Because of the root, a particular tree receives all the information, the water, the water, and for example, the information regarding photosynthesis, everything, all of that happens because of the root. And if the root is not present, basically this tree is dead. Similarly, in a layer 2 network, for a loop free environment in spanning tree protocol, there should be a root switch in the network. Okay, and because it is automatically created, the spanning tree protocol is automatically created, the root switch is also automatically elected. So to elect a root switch, in the network, okay, the first thing that happens is that whichever switch in the network has a lowest priority, spanning tree priority, okay, the spanning tree priority ranges between 1 to 65535, and the default is 32,768. So whichever switch has the lowest priority, it becomes the root switch. And if the priority is a tie, the next tiebreaker is the lowest MAC address. Whichever switch has a lower MAC address becomes the root switch. This is what we had seen in last night's class. So continuing with that discussion, okay, once the root switch is elected, okay, once the root switch is elected, the next step in the spanning tree process is that elect a root port. Elect a root port on all non-root switches. On all non-root switches, elect a root port. So continuing with the same diagram, switch number 1, switch number 2, and switch number 3. These are the three switches. And in last night's class, we discussed switch 1 becomes a root switch because the MAC address is 1111, and MAC address of 2 is 2222, and MAC address of 3 is 3333. Okay. Switch 1 becomes a root switch. So obviously, switch 2 and switch 3 are non-root switches. So on these two non-root switches, we will elect a root port. Now, the question is, what is a root port? Okay. Through the root port, a non-root switch, sends data, sends data to the root switch. That is the port. That port through which a non-root switch sends a data towards the root switch. That particular port is a root port. So in order to explain this, on switch number 2, it has two root ports. One is this one and one is this one, meaning it can send data to the root switch like this, or it can send the data to the root switch like this. So it has two root ports. Similarly, for switch number 3 also, it has two root ports, these two. So it can send the data to the root switch like this, or it can send the data to the root switch like this. So as I have mentioned, elect a root port on all the non-root switches, meaning that if there are multiple root ports, one of them should become the root port. Now we can see that on both these switches, there are two ports which are the contender for the root port. So a root port election should happen. Okay, elect a root port. And how a root port is elected? Root port is elected based on lowest cost to reach the root switch. Lowest cost to reach the root switch. Now, when I say cost, it means the spanning tree protocol cost. Okay. So the lowest spanning tree cost out of these two ports on switch 2, out of these two ports, whichever port has a lower spanning tree cost to reach the root switch will become the root port. Now the question arises, what is spanning tree cost? So spanning tree cost is basically a predefined or standard cost. Let me show you that. Spanning tree interface cost. Okay, so you can see over here, these are the spanning tree cost. In the second column, spanning tree cost 250, 100, 62, 19, 432. These are predefined spanning tree cost. And how are these costs calculated? It is calculated based on the bandwidth. And you can clearly see lesser bandwidth, 4 Mbps, which is the lesser bandwidth in this particular diagram. 4 Mbps has a higher spanning tree cost, whereas the higher bandwidth, that is 10 Gbps, has a lower spanning tree cost. So as your bandwidth increases, your spanning tree cost decreases. And these costs are predefined. You don't have to do anything. Based on the interface, the spanning tree will automatically calculate its interface spanning tree cost. Meaning that, let's say that this is a 4 Mbps link and this is a 2 Gbps link, for example. Okay, so spanning tree will automatically know that this interface will have a cost of 250. Okay, and this interface will have a cost of, what is the cost? Check. For 2 Gbps, the cost is 3. This interface will have a spanning tree cost of 3. It automatically knows. Okay, this is how a spanning tree cost is not calculated, it's predefined and we don't have to do anything. The switch will automatically calculate the spanning tree cost or consider the spanning tree cost themselves. Now, for our understanding purpose, let us assume that the cost of each of these interfaces is 1. Okay, for understanding purpose, let's consider that the cost of each of these interface spanning tree cost is 1. Okay, now let's see how the root port is selected on the non-root switches. So as I said, for switch number 2, it can reach the root switch like this and it can reach the root switch like this. Out of these two, which has a lower cost? Okay, we have to find that out. So to reach the root switch like this, the cost is going to be 1. We will always calculate the cost based on the exit interface cost, not the incoming interface, but the exit interface. So to exit, When it exits out of this interface, the cost is 1. From the other end, the cost is going to be 1. And then again from 3 to 1, again the cost is 1. So 1 plus 1. So from this side, the cost is 1. From this side, the cost is 2. Out of these two, obviously, one is a lower cost than 2. So that means the directly connected interface between switch 1 and switch 2 becomes the root port. This interface becomes the root port. Similarly, for switch number 3 also, this interface would become the root port. Is it clear how a root port is elected?
So it will be which is the minimum cost connected to the root. So root
Not
is
connected to the root, towards the root.
towards, okay,
There may be multiple switches in between also. There will be different
okay,
connectivities out of those connectivity, which has a lower cost to reach, which interface has a lower cost to reach the root switch. That interface will become the root.
okay. So you mean if between 1 and 3, one more switch is there in the box, then what will happen? Then also that here, huh? Now also that will be root port only, that left, right side, that
Yeah,
which
now
is now
that's a good
root port.
question. I'll explain that. So since you have asked, let me explain that. Okay. With this diagram, is it clear which is the root
Yeah,
port?
yeah, with
Yeah.
this.
Yeah. Now, since you brought that up, as I said, now there may be a situation, as you said, okay, this is switch number 1, switch number 2, switch number 3, and switch number 4. Okay. This is a root switch. Okay. For switch number 2, obviously, this will become the root port. For switch number 3 also, this will become the root port, because obviously, let's consider the cost as 1. For all the interface, let's assume the cost. So obviously, this will have a cost of 1. And for switch number 2, this way, this is 1 plus 1 plus 1. So in the other way, the cost is 3, but the direct connectivity has a cost of 1. So obviously, this interface becomes the root port for switch number 2, and the same applies for switch number 3. Now, from switch number 4's perspective, let's try to understand which is going to be the root port. So for switch number 4, this way and this way is also cost of 2. This and this is also cost of 2.
Yeah, both are same then.
Both are same, correct? Both are same. Now, in this scenario, how will switch number 4 decide which needs to be the root port? So in this case, the third criteria comes, not the third criteria. The first criteria is the lowest cost, right? We already know to elect a root port, the criteria is lowest cost. If the cost is also a tie, okay, if cost is also a tie, okay, आयुषी इसको ले जाओ यार. Hmm. So when cost is also a tie, okay, when cost is also a tie, the switch now will find out which neighbor has a lower MAC address. So in this case, for switch number 4, 2 and 3 both are neighbors. Out of these two switches, which switch has a lower MAC address? So obviously, 2 has a lower MAC address, and hence this interface will become a root port.
Okay, so going towards the root, in middle, whichever switch comes, which has the lower MAC, that will become a
Lower MAC,
that side it will become a root port.
root port. Okay. So in the basic first election criteria is lowest cost to reach the root switch. Now, if the cost is also a tie, then whichever neighboring switch has a lower MAC address, that interface becomes the root. Clear? Any question?
Yeah. Yeah, it's clear now.
Now, after a root port is elected, after a root port is elected, the third is elect elect designated ports. Designated ports or DP on all non-root switches. Okay, elect designated port on all non-root switches. So switch number one, switch number two, switch number three. Okay, so this is the root switch. We already know. For switch number two, this is the root port. For switch number three, this is the root port. Okay, now to elect a designated port, okay, the criteria is all ports except the root port are designated. Okay, so that means on switch number two, this is a designated port. On switch number three, this is a designated port. If there are multiple connections, let's say if there are multiple connections, this is going towards this switch, this is going towards this switch, this also becomes a designated. And over here, this also becomes a designated. So all ports except the root port are designated ports. Clear?
Okay, got it. So any number of things, all the ports connected, only remaining other than the root port, everything will become left in the
Everything will
other.
become a
So one is the
everything.
root. So one is the root here, R3.
Yeah,
Okay, so that's
R3.
the
Yeah,
okay. R3 is the
correct.
one, right? So
Yeah,
this side will
R3.
be root port and other. Okay, got it. Other all sides. So what will happen to R3's other ports?
Yeah, that's
So
what. If
that
R3 has multiple connection, that
no,
also
that is
becomes a
that is not
designated.
R3. No, that is not R3. R3 is left side.
R
That is one. That is
root
one.
switch. You mean root switch?
And this one other ports. What? Oh, this one
Yeah,
nothing
yeah,
is
yeah,
there, right? Okay. So
yeah,
this one
yeah,
nothing
yeah,
though.
yeah.
Only that is in other sides. Right? Only
Yeah,
in
as I
two
said,
and
it's
three sides.
see here
Okay,
non-root
okay,
switches,
got it, got it,
non-root switches. Now,
got it.
what about root switches? Okay, so on root switch, all ports are designated ports. Okay, on non-root switches, except the root port, every port is a designated port on non-root switches, and on root switch, all the ports are designated ports. Okay, now we understood how to find out a designated port, or how a spanning tree finds out a designated. But what is the meaning of designated? Just like a root port, through root port, the non-root switches will send data towards the root switch. Okay, this is what I mentioned over here. Root port is the port through which non-root switches sends data towards the root switch. Okay, so switch 2 is sending data towards the root switch through the root port. 3 is also sending data towards the root switch through the root port. Now, that is what a designated port does in the opposite. Using designated ports, all these switches, designated ports is a port which sends data to non-root switches, which sends data to non-root switches. So for a root switch, switch 1 is a root switch. So obviously all the other switches are non-root switch for switch number 1, correct? So this is a designated port. This is a designated port. So it will send, if any data is received by root switch and it wants to forward the data, it will send the data towards the non-root switches to the designated port, to the designated port. Similarly, for switch number three, switch two is a non-root and vice versa. Okay, listen to this very carefully. Switch number 3 is a non-root switch. Switch number 2 is also a non-root switch. But from their perspective, the other switch is a non-root switch. And to reach that non-root switch, they will use their designated port to send data to each other. Clear?
Yes.
Okay. So let's
Because
say
in
that
one topology, only one will be there root, right? So if you add another can't be a root. So only one will be there, and all will be like
yeah,
non.
non-root
And
switches.
everybody will have only DP only there. Only the things, only these two and three which is connected to one, that will have RP, and other all will have any switch there. Suppose 4 5 you have connected two more, right? 4 5 that will have
Yeah.
all the
We'll
ports
bring.
as DP.
I'll bring a bigger picture. I will bring a bigger picture, and then you will understand how things are. Just to keep things simple, I'm just using three like no switches. Now, since you have brought that up, let's say this is 4. This is 4 and this is 5. For 4,
Right.
this will become a root 4 because through this only it will
Oh,
reach the root switch.
okay,
For
there
5,
also
this,
there also root port will. I thought it will
yeah.
be,
As I said, see here
but that is
mentioned,
connected to
el- elect a
non.
root port. No. Elect a root port on all non-root switches. All non-root switches. It may be
Oh,
directly connected.
that
It may not be directly connected.
that means all non-root switches will have one at least minimum root.
One root port. One root
Okay,
port
one minimum
will
it
be
will be
there.
there, and okay, and others will all be this
Yes.
thing. Okay, okay. I thought it that
Other,
all the things will
yeah.
be DP.
So other interfaces,
No, for the four,
So
for
on
number
switch
four.
number 2 over here, on switch number 2, this becomes a DP.
Okay, and number four also, if any other thing is, all
For
will be
number 4,
DP.
because through here it will send the data. Yes. So for switch number 3 and switch number 2, it has two DPs because
Two
through
DPs.
as I have mentioned, through DP only it will send data towards other non-root switches.
Non-root.
Okay,
Okay, non-root it will send. Okay, got it.
non-root switch. So DP, he will send data towards switch number 4 through the DP. Switch number 2 will send the data towards 3 through the DP. Switch number 3 is also sending the data towards the other switch through the designated.
Through the DP. Okay.
Clear?
Clear.
Clear?
Yes.
Any
Yes.
question? Yeah. Let me declutter
No, that
this.
was the doubt. It got clear. I thought it will all be DP, but one root port will be there, and others will be DP. Got it.
Yeah. Okay. Now the last condition. If you see in all these things, still there is a loop present. If you send a data in this particular network, there is a loop. Okay, you have not removed, or the spanning tree has not removed a loop, or it has not created a loop free environment, right? So the fourth step, the final step, is elect a block port. Elect a block port on non-root switches. On non-root switches. Elect a block port on non-root switches. So switch number 1, switch number 2, switch number 3 is connected. This is a root switch. On root switch, this is a designated port. This is a designated port. This on switch number 2 is a root port. On switch number 3, this is a root port. And on switch number 3, this is a designated port. On switch number 2, this is also designated. Okay, this is what we have the diagram as of now. Now, elect a block port on non-root switches. Now, the criteria to elect a block port is not a criteria, the condition is that a block port is elected where there is a DP to DP interface connectivity. That is where you will elect a block. This is the first and foremost condition. That
And this is not clear
the
actually what is this telling.
yeah. I'm mentioning that the block port is elected where there is a DP to DP connectivity, designated port to designated port connectivity. like the one between switch 2 and 3.
Okay. Okay, so
Okay,
it will
that
not
is
be
where,
selected towards the route. It will not be selected towards the route, but other side of the route which is connected through the
correct,
DP. Okay.
through the DP only. And the condition is again, it should be a designated port to designated port connectivity. It can be a designated port to root port connectivity. No, there a block port is not elected.
No, so never it
Okay,
will be like this. So these two rows, it will never
it
be
will,
block port.
yeah, it is
RPDP,
always,
RPD.
yes, it is always a DP and DP, always. It is not
This
DP and RP. Like you can
these
see over
points
here,
need to be
DP and
remembered.
RP. Over here, you can see this is DP and this is RP. You cannot elect a block port there, or a spanning tree will not elect a block port there. Where will the spanning tree elect a block port? It will always elect a block port when the two switches are connected through their designated port interfaces.
With that too, it can be now any other side. It can be either towards the 2 or towards the 4, 3.
Yeah, correct. Now, over here, we can see that 2 is also a designated port, 3 is also designated. Now, how is a block port elected? One of them has to like block the interface. So the criteria is higher spanning tree protocol cost is going to change its interface to block port, change its designated port interface, change its designated port interface to block. If the cost is a tie, then higher MAC address switch will change its designated port to block. This is the condition. So between switch 2 and 3, they will find out which has a higher cost, spanning tree cost to reach the root switch. So for switch number 2, the cost is 1. Switch number 3 also, the cost is 1. So cost is a tie. Both of them have the same cost, and hence there is no switch which has a higher spanning tree cost to reach the root switch,
They
which
are
may
going to they are going to block the DP port, right? Not this RP port. So why they are
yeah
checking
yeah
this one?
yeah. Let me complete the whole thing. So first they'll find out either of among them which switch has a higher cost to reach the root switch. So in this scenario, two two's cost and three's cost to reach the root switch is same. So that's a tie. Right? Then if the cost is a tie, the next is which switch has a higher MAC. Okay, that switch will convert its designated port to block. So out of switch 2 and switch 3 has a higher MAC address. Switch 3 has a higher MAC address, and hence switch 3 will convert its designated port into a block. So this interface will be blocked. And when this interface gets blocked, though it's physically present, but virtually there is no link present. So switch 1, switch 2, switch 3, right? This is a designated port. This is a designated port. This is a root switch. Switch number 2 is root port. Switch number 3 is root port. Switch number 2 is designated port. And switch number 3 is block. And hence, with this, the spanning tree has created a loop-free environment. So it's not like when there is a DP to DP connectivity, both the interfaces will go block. No, one of them has to go into a blocking mode. And the criteria to go into a blocking mode is which switch has a higher spanning tree cost. Whichever switch has a higher spanning tree cost, it will change its designated port to block. And if the cost is a tie, which switch has a higher MAC address, that switch will convert its uh, designated port to a block. Clear? Any question with
Yeah, clear.
block port? Okay. Now let's
And the same thing will happen in the case of the four switches that connected in the one more case was there at above.
Yeah,
So
yeah, yeah. We'll like uh, create a bigger diagram, and then let's see how things happen. Okay. So
no, it's a very big diagram.
okay, something like this, random diagram. Okay. So we have 9 switches, right? We have
So the
9 switches.
okay, those like MAC address will be 111.222.555
Yeah, yeah,
like that.
yes, yes. 111.222.333 MAC addresses, and we are assuming the spanning tree priority to be 32,768. Okay. MAC addresses 111.222.333, etc. MAC address like 111.222.333, etc. like that. Okay. And the spanning tree cost of each interface is 1. This is our assumption. Okay. These are our assumption for this diagram. Okay. And now we have to find out a loop-free environment. Now, not we have to find out how spanning tree will create a loop-free environment. All right. Now, we know that the first criteria is root switch. Find out the root switch. To elect a root switch, we know that out of these switches, whichever switch has a lower spanning tree cost becomes the root switch. And since we have assumed that the spanning tree cost is 32,768 with all these switches, that's a tie. If spanning tree cost is a tie, the next tiebreaker for the root switch is the lower MAC address. Correct? So here, elect a root switch, lowest spanning tree priority. And if the spanning tree priority is a type, then the lower MAC address switch will become the root switch. So in here, since we have assumed 111.222.333, etc., those MAC addresses, so obviously our switch number 1 becomes the root switch. Is this clear?
Yeah, this is clear. Now, if those things are different, then it will become difficult to like if that it is not 32978 and MAC address goes different, then it will
Yeah,
become
yeah,
difficult to
obviously,
identify.
obviously. Yeah, okay.
Here it was very easy, right? It is same, and then this one came as 1111, so we know that
Right,
exactly.
right. Yeah, yeah. I mean, obviously, when you are working in a real-time scenario, you will read the MAC addresses, and comparing the MAC addresses is also very easy. Okay, when we do the practical for spanning tree protocol, you will clearly see how the switches are identifying the roots. Okay, through the MAC addresses. It's very easy to find that out. Okay, so here switch 1 becomes the root switch. Now the second is elect root port on all non-root switches. Right, that was the second criteria. And how was the root port elected? Okay, so whichever interface on non-root switch has a lower spanning tree cost to reach the root switch, it becomes the root port. Right, lower spanning tree protocol cost to reach the root switch. That interface becomes the root port.
Yes,
So
right.
let's start from 2. After 1, let's start from 1. Sorry, let's go to 2. So okay, now yeah. So for 2, it has multiple ways to reach the root switch, which has a lower cost. And as I said, we have assumed the cost to be 1 for every interface, right? So let's see the direct connectivity. This is 1 plus 1, 2 plus 1, 3 plus 1, 4. Total cost is 4 to this. Okay. Here you have 1, 2, 3, 4. Again, this is a tie, right? Then you have this connectivity 1, 2, and 3. Okay. So you have 1, 2, 3, 4. Okay. 4 is the maximum cost that you can see through this thing. Through here also 1, 2, 3, and 4. Again, 4 is a tie, right? Then we do have other links as well. We have 1, this is the direct towards 9, then 2, then 3. So now 3 is a lower cost. Do we have any other combination? Do you have any other combination? So we have 1, 2, 3. This also is a tie for cost of 3. Okay. So from here, here, and here, this was 3. Then 1, 2, then 3. This was also 3. Cost of 3. Tie. Right. Do we have any other combination which is less than 3? 1, 2,
P
3, 4.
P1 more is there in the top, right? You go from second to 9, 9 to 1, 9 to this top row.
1,
That also is 3.
2, 3. Yeah. So we have 3 interfaces. Okay. Through which it can be a like what do you say, root port. Okay. Obviously there are 2 interfaces which can become a root port. Either this interface will become a root port or this interface will become a root port. Now we have to find out which will become a root port. So again, 3 is a tie, right? 3 is a tie, right? Now when it finds out that 3 is a tie, cost of 3 is a tie, the second tiebreaker is which neighboring switch has a lower MAC address. Which neighboring switch has a lower MAC address? Obviously, 6 has a lower MAC address. So if you see, for 2, 9 is a direct neighbor, 6 is a direct neighbor. Obviously, from 6's MAC address is lower than that of 9. So obviously, this interface becomes the root port. This interface becomes the root port. And let me just write the legend. Black dot means root port. Okay. So on 2, this interface is the root port. So it will go to 6, then it will go to 4, then it will go to 1. It does not care from here, it has 2 paths. Via 9, it has 2 paths. It does not matter. It doesn't matter because from after 9, you have this way and then you have this way. It doesn't matter because the directly connected switch, it will check only the directly connected switches MAC addresses. So in this case, 6 has a lower MAC address than that of 9. So that is why this interface becomes the root. Clear? Any question?
Yeah, this is clear.
Now for 3, next is 3. Obviously, the directly connected interface will become the root port, right? That's the obvious choice, right? Then 4. For 4 also, the directly connected interface becomes the root switch. Then for 5, let's see for 5, you have 1, 2, 3. This is 3 is the lowest cost as of now. Then you have 1, 2, 3. Again, so you have 2 interfaces with a cost of 3.
One more
So
is
out
there.
of these, huh?
One more is there.
One more
5
is there,
to
but
9.
then, but
No,
5
5 to
to,
9, 9 to 4, and then 4 to 1.
and then that's a higher cost. Huh? Why would it choose?
No, it is the same 3 only, right? 5 to 4, 5 to 9, 9 to this
5
one,
to 9,
9 to
then
7, 7 to 1. That is 1.
yeah, yeah, this
5
is
to
1.
9, 9 to 4, 5 to 9, 9 to 4, and this one.
5 to 9, 9 to 4. Okay, yeah. Then
And
5 to 6.
4, and then 1. This is the
Yeah,
same only, right?
same. Okay. So again, which has a, so 3 is a tie. When 3 is a tie, the next thing comes which has a lower MAC address, which neighboring switch has a lower MAC address. So obviously 6 has a lower MAC address, and hence this interface becomes the clear.
Yeah, clear.
So from 5, it will go to 4, then it will send it to the root switch. Clear? Now, next from 5, then 6. For 6, for 6, we can see this is the lowest one, 1, then 2, directly 2, 1. Right? So for 6, this interface is the root port. 6, then 7. For 7, directly connected interface becomes the root port. For 8, it has two way to reach, like this, then the other is like this. Both are the same, 2, with a cost of 2. Then again 8 will see which has a lower MAC address. Out
Will
of
go
7,
3.
between 7 and
Towards 3 it will go. So
towards 3. This interface becomes the root port. Now next is 9. Okay, for 9 again, which is the root port? We have 1, then 2, then again 1, then 2. So again the cost is a tie. And the cost is tied, lower MAC address. Neighboring switch is lower MAC address. Obviously, this 4 has a lower MAC address than that of 7. So obviously, this interface becomes the root. Clear?
yeah,
This
clear.
is how a root port is elected by the spanning tree protocol on all the non-root switches. Okay. Then the next, third, designated port on all non-root switches. We know that on non-root switches, every other port,
Other than
other
the root port. Yeah.
root port is a designated port.
Yeah,
Okay,
so directly
so
we
let
can work.
me change the color. Something else. Let me take that as a purple. So purple or violet, whatever. This is the designated port. Okay, the color is pretty much the same. With that as yellow. This is your designated port. Okay. So on root switches, we know that every interface is a root port. Sorry, designated port. Okay. Then on 2, this becomes designated port 3, designated port 4, DP, DP, DP 5. This is DP, DP 6, DP, DP, DP 6, 7, DP, DP, and 8, DP, DP 9, DP, DP, and DP. Okay, clear? Any question?
No, till here it is clear.
Yeah. Now the last. Find out block port
Okay, this is the difficult part.
on non-root switches. On non-root switches, find out the block. And the condition is wherever the link is DP-DP connectivity, there you will find out the block. Okay. Now, when there is a DP-DP connectivity, we know that first it will look for higher cost. Whichever switch has a higher cost, it should convert its designated port to block. The cost is a type, then higher MAC address. Whichever switch has a higher MAC address should convert its designated port to block port, higher MAC address. Now let's start one by one. Okay, from 1 to 3, it's there. There is no DP-DP connectivity. It's a root port and a designated port connectivity. From again root switch, this is DP-RP. Here also designated port, root port connectivity. So you can clearly see this is a very good example where you can clearly see to a root switch, you cannot have a block port. If you're directly connected to the root switch, you cannot have a block port. Clear?
It has to be okay. It has to be always.
It has to be a root port only. The interface that is directly connected to the root switch has to be a root port. On switch 3, you can see this is a root port. On switch 7, you can see it's a root port. On switch number 4, you can see a root port. So if the non-root switch is, if one of the interface of a non-root switch is directly connected to the root switch, that interface is a root port. Clear?
Yeah, it's
Okay.
clear.
Now let's go to 2. For 2, we have between 2 and 6. No. Between 2 and 9. Yes. So between 2 and 9, we have a DP-DP. Now here, between 9 and 2, one of them has to change its interface to a block port. Okay. So the criteria is whichever switch has a higher cost. Okay. Let's check from 9's perspective. 1, 2. Okay. For 6, sorry, it will take this one. 1, 2. Okay. Because it will reach the root switch through the root port on, right? Not through designated. So 1, 2. Okay. For switch number 2, again 1, 2, 3. So 9, so not 9, 2 has a higher cost to reach the root switch. 2 has a higher cost to reach the root switch, and hence 2 will convert its DP into a block port. Clear? This is a block port.
Okay. So
Now,
why we selected this between 2 to 9? We can select
because
from 2 to 5 also to
yeah,
block anyone.
correct. We will select between 2 to 5 also.
Oh, everywhere to check this.
Yeah. Wherever there is a DP connectivity, you have to
Okay,
convert.
in each of the links we have to check it. That means
Yes.
each place one will be blocked.
Yes.
Okay. So in the bigger
Now,
diagram is much clear. In the smaller diagram, it was like only one was there, right? So it was not clear.
right. So between 5 and 2, which has a higher cost to reach the root switch. Let's check 1, 2, 3. For this one, 1, 2, 3. Cost is a tie. For both of them, cost is a tie. Now, when cost is a tie, which switch has a higher MAC? Obviously, 5 has a higher MAC address, and hence 5 will convert its interface to a block port. Okay. Now,
Got it.
2 is over. Let's go to 3. Between 3 and 8, no DP. Between 3 and 4, yes. Between 3 and 4, there is a DP-DP connectivity. So 3 is direct connectivity and 4 is direct connectivity. That's a tie. Out of 3 and 4, which has a higher MAC? Obviously 4. So 4 will convert its interface to a block. Right? Now let's go to 4. 4 and 9, no DP-DP. 4 and 6, no DP-DP. 4 and 3, DP-DP is there, which we have already seen. Then let's go to 5. 5 and 2, that DP-DP is over. 5 and 9 also have a DP to DP connectivity. Now, which has a higher cost to reach the root switch? 9, let's check 1 and 2. For 5, this is 1, 2, and 3. So 5's cost to reach the root switch is higher than that of 9. And hence, 5 will convert its interface to a block. All right. Now, let's go to 6. Between 6 and 2, nothing. Between 6 and 5, nothing. Between 6 and 8, yes, there is a block port. There is a DP-DP connectivity. So from 8, 1, 2. Okay. Then for 6 also, 1 and 2. So cost is a tie. And cost is a tie, which switch has a higher MAC address. 8 has a higher MAC address than that of 6, and hence 8 will block its designated port into a block port, convert its designated port to a block. So 6 is also done. Then let's go to 7. Between 7 and 9, yes. 7 and 9, there is a DP-DP connectivity, and obviously 7 is directly connected to 1. So its cost is going to be lower, and 9's cost is going to be higher. And hence 9 will convert its interface to a block. So 7 is also done. 8, yeah. Between 8 and 7, there is also TP-TP connectivity. 7 is directly connected and 8 will have a higher cost, correct? So 8 will convert its interface to a block port. Then 9, last one. So 9 is almost done with every other connectivity. So now let me remove the links where you have a block port. This is your loop free network. So this is your loop free network. So on this blocked interface, your data will not be received. It will not be also transmitted. The data on your block port will never be received, will never be transmitted. So you may wonder, what if 5 wants to send data to 3, right? What if 5 wants to send data to 3? It will take this path only, like this.
So everybody will have only one path to go to anywhere.
Yes. Okay. So if 3 wants to send data to, let's say, 6, okay, it will send data like this. It will send data like this. Okay. And this is how a spanning tree protocol creates a loop-free environment.
So any kind of complex graph will be there. It will convert it to a single this kind of thing.
Yes.
One connection.
Yes. Correct. Clear? Any question?
Yeah, clear.
Now, if you had noticed, everything, whatever we did here, was based on the root switch. See, root switch, we know, based on the lower priority or the MAC address. Root port was selected based on the cost to reach the root switch. Designated port, it's okay. But again, block port was based on the cost to reach the root switch. So the placement of the root switch is very, very important. Okay. Obviously, you do not have the control of where the root switch will be placed, because root switch is elected based on the spanning tree priority and MAC address. We don't know which switch will have a MAC address lower than the other devices, right? So what if this switch over here was the root switch? Switch number 4 was the root switch. So based on switch number 4 and other switches reachability towards switch number 4, a different loop free network will be seen. I hope you get this point.
Okay. So if now we remove the cables from switch 1, which is root, and then we connect the one beside 5, the cables, and then again everything will change.
Correct.
So if the one we remove the cables from the one, it is connected to 7, 4, and 3, those 3 cables, and then I connect the one to this side to 5,
Right.
2, and somewhat to 9.
Yeah.
Somewhere.
So let's say, for example, if this switch is the root switch, for example, 5's MAC address is lower than the whole network. This switch becomes a root switch. Then your network will completely change.
Yeah, the path, block port, and all those things.
Block port, designated port, root port will completely change. Okay. Clear?
Yeah, clear.
So this is how a spanning tree protocol creates a loop-free environment automatically. As I said, we don't have to do anything, but I explained you this process in order to understand how spanning tree basically finds out a loop-free environment. So in a network, in a Cisco switch network, right? Spanning tree protocol is enabled by default. Okay, so Spanning tree is enabled by default on all these Cisco switches. I'm not sure about other vendor switches, but on Cisco switches, spanning tree protocol is enabled by default. So let's assume this same scenario. When these switches, Cisco switches, are connected together, you don't have to do anything. Spanning tree is enabled. No matter how you connect these switches, spanning tree will run. It will find out a loop-free environment. It will find out a loop-free environment for you. Clear?
Yeah, clear. So automatically it will do that thing, right? It will keep
Yes,
running and
automatically. Yes, automatically it will do. All right. Now let's take example of switch number 8. Let's take the example of switch. What if this interface goes? Either from switch 3's perspective or switch 8's perspective, this interface goes down. So you can clearly see switch 8 is completely isolated. Right? It is completely isolated. Right? Now this
completely
discussion is,
isolated means completely isolated. Okay, yeah,
it was connected like this. It was
okay.
connected like this earlier. If for some reason this interface goes down or there is some problem on that link, so you can clearly see switch number 8 is isolated. It has no reachability to other switches.
Sound was gone. Sound
Huh?
was gone for
Sorry.
some time. Sound was gone for some time.
All
What
right.
was
All
that?
right. Yeah. So I
Yeah.
was saying previously the connectivity was like this. All right. Now, for some reason, the interface between 8 and 3 goes down. And you can clearly see that switch number 8 is isolated. It cannot reach other switches, nor the other switches can reach switch number 8. Correct? I hope you get this point.
Yeah, it was already blocked and now the connection also is gone.
Right. Now, what will switch number 8 do? We'll discuss this tomorrow. What switch number 8 is going to do in such a scenario.
Okay.
All right. So that discussion is for tomorrow. But before that discussion, whatever I showed you, how a
Mhm.
spanning tree works, we'll see that in practical tomorrow. Before I
Okay,
jump
first
into this discussion.
okay, first the lab and then after this one. Okay, fine.
Yes. Yes. All right.
Okay. Yeah. Thanks. Thanks a lot.
Thank you. Okay. So
Okay,
I'll see
yeah,
you
yeah.
tomorrow. Yeah. Bye
Sure,
bye.
yeah, okay, yeah. Good night.
Good night.